Question number 15 in the JEE Main paper of 2013 contains information regarding what is known as a heat engine. And so let us briefly revise what exactly a heat engine does. The functioning of a heat engine is as follows. You have a hot reservoir, and this hot reservoir supplies heat to the gas. The gas is also called the working fluid. So this heat, I'll call it Q1. Now the working fluid, it undergoes a thermodynamic cycle, which in an idealized form can be plotted on a PV diagram. In this thermodynamic cycle, the working fluid converts this heat into two things. It does net work on the surroundings, so that is one sphere where Q1 is used up, and the balance is given as Q2, heat to the surroundings, and the surroundings means it is actually given to technically what is called a cold reservoir. So what that would mean is the working fluid in a nutshell extracts heat from a hot reservoir, gives out work to the surroundings, net work, and in the process also loses some heat to the cold reservoir. Now the next question which may arise is, where do these quantities Q1 and Q2 and W net, where do they appear in the PV diagram which we plot for the heat engine? So to answer this question, I will just plot a hypothetical PV diagram for some heat engine. So let's plot P on this axis and V on this axis, and maybe there is a hypothetical heat engine which operates according to this particular cycle. So this is one particular part of the cycle. That's obviously an isochoric process, and then maybe I have an adiabatic curve like that. It's adiabatic compression because the volume is decreasing, and maybe I have an isochoric process like this, constant volume. Then I may have an isobaric process, constant pressure, something like that. And finally I may end the cycle by drawing another adiabatic curve like this. So that's the complete process. It's just a hypothetical process. Now the question was, where do these things appear? Where is Q1, where is Q2, and where is W net? So W net, it is basically the net work done by the gas during one cycle. Note that in certain parts of the cycle, work may be done on the gas, and in other parts of the cycle work may be done by the gas. So let us just investigate this particular cycle. Clearly, work is done by the gas when it expands, that is when its volume increases. So let's look at the parts of the cycle where the volume of the gas is increasing. It's here. Work is done by the gas on the surroundings. Another way to look at it is the area underneath the PV diagram gives the work done by the gas, and this area is positive surely. So the work done is by the gas on the surroundings. Likewise, positive work is done by the gas on the surroundings in this part of the cycle. Now in this part of the cycle, since the volume never changes of the gas does zero work. Likewise, the gas does zero work over here. And finally, in this part of the cycle, since the volume of the gas decreases, work done by the gas on the surroundings is negative, or you could say that work is done on the gas, positive work is done on the gas by the surroundings. Another way of saying this is, if the work done by the gas on the surroundings is W1 in this part of the cycle, W2 here, W3 here, W4 here, and W5 here, then W3 is equal to 0, W5 is equal to 0. Remember, W I have defined as the work done by the gas on the surroundings, so W1 is positive, W2 is positive, and W4 is negative. Now what would be the net work done by the gas on the surroundings, let us say? So the net work would be W1 plus W2 plus W3 plus W4 plus W5. So of course W3 and W5, they would not contribute towards the net work. W1 and W2 are positive. W4 has to be taken along with the sign, so it's negative. So W1 plus W2 plus W4 would be the net work done by the gas on the surroundings. So we have now understood where W net appears in the diagram. Another way of locating or finding out W net from the PV diagram is to find what is the net area underneath the graph, which basically means that you have to go on summing the areas underneath every part of the cycle. So if I call this particular part of the cycle number 1, then this area, it's a positive area, and if this is 2, then this positive area. Now this is 3, it has no area underneath it, and 4 of course has this area underneath it, which is treated to be negative because the graph goes from right to left, and 5 has no area underneath it. So if I sum these areas, I get 2 positive areas underneath 1 and 2 and 1 negative area underneath 4. So it would mean that I'm basically calculating this area. So the area inside the cycle in the PV diagram would also give me W net. The next thing we want to look for in the diagram is, where do I find Q1? Remember, Q1 is the heat which is supplied to the gas. So if you look at each of these 5 parts of the cycle, for example, we just said that this is an adiabatic process. It's just an assumption for the sake of the example. So heat is neither given to the gas nor is it extracted. So this is of course out of question. I'm not going to look for Q1 over here. Similarly, we just said that this is assumed to be an adiabatic process for the sake of the example, so Q1 is not over here. Now we don't want to go into the details. You have to actually, in the remaining 3 parts of the cycle, that is this one and this one and this one, you have to look for places where heat is extracted and where heat is given. If heat is given to the gas, then of course it's going to be a part of Q1. So without actually doing any detailed calculations, just for the sake of the explanation, let me assume that you discover that heat is given to the gas during this particular isocore. That heat I'll call Qx, and likewise suppose you discover that heat is also given to the gas during this particular isobar, and that heat is Qy, and you discover that heat is extracted from the gas during this particular isocore, so heat is coming out, I call it Qz. Now Q1 is the total heat which is applied to the gas during the entire cycle, so obviously it's going to be Qx plus Qy, and Q2 is the total heat which is extracted from the gas during the cycle, so obviously that's going to be Qz. So this is where you find Q1 and Q2 in the thermodynamic cycle diagram drawn for a heat engine. Now finally, You can also calculate W net if you know Q1 and Q2 by the first law of thermodynamics. So the first law states that the total heat supplied to the gas is equal to the change in the internal energy of the gas plus the work done by the gas. Now we note that we are describing here a thermodynamic cycle, and therefore the change in the internal energy will be equal to 0 because it's a cycle. Now delta Q, the net heat supplied to the gas during the cycle, will be Q1 minus Q2, and the work done by the gas is what we have called W net. So another way of calculating W net is going to be the total heat supplied to the gas minus the heat extracted, or it is the net heat supplied to the gas which is converted to work. The efficiency of a heat engine finally is given by the work done, the net work done by the gas, divided by the heat Q1 which is supplied. It's not the net heat, it is the heat supplied by the hot reservoir. So this efficiency can be calculated by substituting for W net by gas as Q1 minus Q2, and then I divide it by my heat input which is Q1. So it turns out that it is 1 minus Q2 divided by Q1. If I multiply this by 100, then I get the percentage efficiency. So this particular cycle, thermodynamic cycle, which corresponds to a heat engine, will also tell you how to calculate the efficiency of the heat engine. You can always derive this particular formula in the examination. Right, so now let's actually look at the question which appeared in the JEE Main 2013 paper. So the question gives this sort of diagram. It's a thermodynamic cycle in a PV diagram, and it says that this particular diagram represents the thermodynamic cycle of an engine operating with an ideal monatomic gas. And we have been asked what is the amount of heat extracted, of course by the gas, from the source in one cycle. Now by the source, what is meant is the following. If you look at this picture block diagram of a heat engine, the source of heat would be the hot reservoir. So basically, when it is asked to find the amount of heat extracted from the source, they are asking you what is the value of Q1. So remember, to find Q1, you must identify which of these branches, I'll call them 1, 2, 3 and 4, correspond to heat being supplied to the gas. So to do that, the easiest way according to me is to repeatedly apply the first law of thermodynamics to each branch of the cycle. So the heat supplied to the gas is going to be delta E internal of the gas plus the work done by the gas on the surroundings. So it's easy to find the sign of delta E internal, at least sometimes, and it's easy to find the sign of the work done by the gas, and when I add these two, it might help me to find whether the heat supplied is positive or negative. And remember, we are interested in those branches where the heat supplied is positive. So let's look at branch number 1 first. That is to say, this particular branch. Notice that branch number 1 is an isochore. The volume doesn't change. So the work done by the gas must be equal to 0. Now let's look at delta E internal. Now delta E internal, whether it is positive or negative, can be found out by finding the sign of delta T, the change in temperature of the gas. Remember, if the temperature of the gas rises, that is if delta T is larger than 0, then delta E internal must necessarily be greater than 0. So how do I find whether the temperature of a gas rises or not? There are several ways to do it, but one way is to draw isotherms, that is curves of constant temperature passing through the two endpoints of the process. So there will be two isotherms. One isotherm would be like that. Remember, an isotherm is a hyperbola because T equal to constant would correspond to PV equal to constant. So the graph would be of that nature. And the second isotherm passing through the other extreme point of the branch 1 is that one, the dotted isotherm. Actually, there is a small correction in the second isotherm. The equation of the second isotherm is as usual PV is equal to constant. But if you look at the lower right hand side vertex of the rectangle through which the isotherm passes, the pressure is P0 and the volume is twice V0. And hence the product of P and V is 2 P0 V0. Likewise, if you go to the left hand side top vertex of the same rectangle, then the pressure there is 2 P0 and the volume is V0. So the product of pressure and volume at that point is once again 2 P0 V0. Now this implies that the left hand side top vertex of the rectangle must also lie on that isotherm, and so the second dotted hyperbola which has been drawn must actually pass through the left hand side top vertex of the rectangle. However, later on when we are going to use this hyperbola, we are only going to use the fact that it is lower than the other hyperbola drawn in the diagram. And similarly, when we use the dotted hyperbola in another part of the problem, it is going to be above another hyperbola which we draw. In other words, the small mistake which has been made right here does not really affect the solution. So now we also know that this particular isotherm corresponds to a low temperature. This one corresponds to a high temperature. So as the isotherms they go away and away from the origin, the temperature rises. So we know that in process number 1, the temperature of the gas falls. It goes from a high level to a low level. That would mean that delta E internal is negative. Now that would basically mean that Q supplied to the gas is negative, which means that during process number 1, the gas supplies heat to the surroundings. So I have named this something, I call it QA. QA is the heat which is given to the surroundings by the gas during step number 1. Now let's look at step number 2. So step number 2 is an isobar, and you see that the volume of the gas is decreasing during step number 2. So obviously the work done by the gas is negative. Now if you look at the isotherms passing through the initial point and the final point, this one, sorry, you see that the temperature is decreasing because the gas is going from a higher isotherm, this one, to a lower isotherm, this one. So delta E internal must be negative. That means that the Q supplied to the gas is negative, which would mean that the gas supplies positive heat to the surroundings. That would be QB. Now when I say that heat is applied to the surroundings, QA plus QB up till now, I mean supplied to the cold reservoir. Now let's look at step number 3. In step number 3, it is a isochore, so work done is equal to 0. And further, the gas is going from a lower isotherm to a higher isotherm, so temperature is rising, so delta E internal is definitely greater than 0, positive. So Q supplied is positive. During step number 3, we are supplying some heat to the gas. So that heat which is supplied to the gas, I'll call it QC. And finally we look at step 4. Now step 4 is again an isobar, and the work done during step 4 is the area underneath line 4 or line segment 4. The line segment goes from left to right, so obviously the work done is positive. It's an isobaric expansion, so this is greater than 0. Now let's look at delta E internal. This is the isotherm on which the gas is initially, and this is the final isotherm. So it's going from a lower isotherm to a higher isotherm, which means that the temperature is rising, which means that delta E internal is positive and Q supplied is also positive. So the heat which is supplied to the gas during step 4, it's positive, and I'll call that QD. Now if you look at the question, you have to find the amount of heat extracted by the gas from the source. So once again, I'll draw your attention to what we have to find. We have to find this Q1. Now Q1 is of course the heat supplied by the hot reservoir to the working fluid or to the gas. It's not the net heat supplied. We don't want Q1 minus Q2. You want the heat supplied by the source, so you just want Q1. So what you do, as we have already done, is to identify the branches where heat is supplied to the gas. So it's branch number 3 where QC is supplied, and branch number 4 where QD is supplied, and Q1, which is what we want to find, is actually QC plus QD, and QC plus QD would be the answer to the question. Now let's try to find QC. QC is the heat supplied to the gas during an isochoric process, and since the volume doesn't change, the heat supplied to the gas is simply N times CV times delta T, and that can also be written as N times, now CV, since it is given to be a monatomic gas, is 1.5 R, and times delta T. And since delta T is not directly given, we just rearrange this as follows. We say it's 1.5 into NR delta T, and we realize that since PV is equal to nRT always, therefore delta PV is NR delta T. So what I get is QC is 1.5 times delta P into V, which is 1.5 times P final V final. So we are talking about this particular point where the final pressure is 2P0 and the final volume is just V0 minus the initial value of P into V. It corresponds to this point, so P0 times V0. So this is nothing but 1.5 times P0 V0. Now we find QD. QD can be found by several methods. For example, you can apply the first law of thermodynamics and evaluate QD by first finding the work done during process 4 by the area underneath the that particular curve or that particular line, and you also find delta E internal by a process similar to how we found delta E internal for this particular process, that is process number 3, because in process number 3 QC was nothing but delta E internal. It's an isochoric process. But the easier way to do it, to find QD, is to realize that step number 4 is isobaric. So QD is going to be N times Cp times delta T, which is therefore going to be equal to N times, now Cp for a monatomic gas is 5 by 2 R times delta T, and that turns out to be 5 by 2 multiplied by nR delta T, which is 5 by 2 times delta PV. Now that's going to be 5 by 2 times PV final. So we are talking about this point. PV final is 2P0 times 2V0 minus PV initial. We are talking about this point, which is 2P0 V0. So this turns out to be 5P0 V0. That's QD. Now QD I must add to QC to get the total heat supplied. So total heat supplied Q1 is QC plus QD, which is 6.5 P0 V0, which is one of the options given, 13 by 2 times P0 V0. So that would be the heat supplied to the working fluid, that is to the gas, by the source, that is by the hot reservoir.